Okay, this is Web Assigned 6F, number 17. And it says, a space station is constructed in the shape of a hollow ring of mass 4.35 times 10 to the 4th kilograms. Members of the crew walk on a deck formed by the inner surface of the outer cylinder wall of the ring, with a radius 130 meters. At rest, when constructed, the ring is set rotating about its axis so that the people inside experience an effective free-fall acceleration equal to g. The rotation is achieved by firing two small rockets attached tangentially to opposite points on the rim of the ring. So, part A asks to find the angular momentum. What angular momentum does the space station acquire? So we know that angular momentum, L, is equal to the moment of inertia times the angular velocity. So, and we can find both of these. So, we know the moment of inertia, since it's a ring, is equal to mr squared. So then we can just plug this stuff in. It gives us m, so 4.35 times 10 to the 4th kilograms. Times r, which was 130 meters. That's squared. So plug this in, you get 7.35 times 10 to the 8th. And then for the angular velocity, we know that the centripetal acceleration it gives us was equal to g, so 9.81. So we can say that r times angular velocity squared is equal to the centripetal acceleration, so 9.81. So we know r, which is 130 meters, so then we can just solve for the angular acceleration. So it would just be equal to the square root of 30. And this will be equal to 0.27 rads per second. So now we can just plug both of these that we just found into here. So it's here. So we got I was equal to 7.35 times 10 to the 8th times 0.27. And we get that the angular momentum is equal to 1.98 times 10 to the 8th. That'd be kilograms times meters squared over seconds. So this is the answer to part A. And part B asks, for what time interval must the rockets be fired if each exerts a thrust of 130 newtons? So, okay, so for part B, we'll do it down here. So we know that the torque is equal to F times R, F cross R, F times R. So we can do it for each one basically. We can do F times R plus F times R because there are two rockets, so 2FR is basically what we get. So we're looking for time, but we can use this torque to find the angular acceleration, which we'll need because we need to find time. We have the angular velocity, but we need to find the angular acceleration. So, and torque, because torque is also equal to I alpha. So 2 times R, so if we plug stuff in, we know they were both 130 newtons, so we plug in 130 newtons for the force. And R was 130 meters, so we plug in 130 there. So now we get that the torque is equal to 33,800 newton meters. So now we can plug this in up here because we know I, so we're going to solve for alpha, so 33,800 is equal to I was 7.35 times 10 to the 8th times okay. And solving this, we get that the angular acceleration is equal to 4.599 times 10 to the negative fifth radians per second squared. So now we can plug this in, so we know that angular velocity is equal to angular acceleration times time. So now we just solve for time. We divide the angular velocity by the angular acceleration. So once we plug this in, 0.27 rads per second over 4.599 times 10 to the negative fifth rads per second squared. All this, get time is equal to 5871.3 seconds. And this is your final answer for B. So basically, just remember that the angular. This is the hard part. The angular setting the centripetal acceleration equal to r times the angular velocity squared. Which some people don't get. Like some people like get tripped up because they don't know what the acceleration is. Because even though it says that it's equal to g, like they don't know if that's like the tangential acceleration or something like that. Like, but either way, it's like that. So, and basically what I learned from doing this problem is that you can use torque. You can use like multiple forces and torque together to help solve for something like time. That can help you find like time. You can use torque to find time, and then not directly though, but you can use it to find like the angular acceleration, which can then help you to find like a quantity like time. So, and then also like I learned how to use angular momentum, how to find angular momentum through this problem by setting I equal to omega, or setting angular momentum equal to I times omega. So yeah.